11,500 feet is the minimum elevation where the oxygen thins and the Himalayan peaks become a permanent barrier to movement. At this altitude, the population was once tethered to the singular and treacherous Zojila mountain pass as their only lifeline. Why was such a high-altitude passage considered one of the most unreliable routes in the world? A mere 2 or 3 hours of intense snowfall could bury the entire path, erasing the only transport artery from the map for several consecutive months, and leaving the region beyond the ridge in absolute isolation. But the era of total dependence on surface weather has ended. Modern engineering has opted for a bolder trajectory by cutting a path directly through the ancient rock. The Zojila Tunnel represents a massive excavation effort, reaching a length of over 8.7 miles deep beneath the Himalayan massif. This underground corridor ensures that vehicular traffic continues to flow regardless of ice accumulation, sudden landslides, or the onset of extreme winter storms. One can notice how the drilling rigs penetrate the geologically complex layers of the mountain with rhythmic precision. The equipment gradually advances through shifting strata where the pressure of the rock is immense. It gets more complex further on. Engineers must account for the unpredictable nature of the tectonic plates while maintaining a stable environment for the tunnel boring machines. Because the terrain is among the harshest on the planet, every meter of progress requires constant structural reinforcement. It seems simple to follow a straight line through the peak, but in reality, the geological diversity of the Himalayas makes every foot of excavation a technical challenge. At first glance, the rock appears solid, but internal stresses can cause sudden collapses if the support systems are not installed with jewelry-like accuracy. The process is only gaining momentum as construction crews work in shifts to battle the high-altitude environment. Huge ventilation systems circulate air through the 8.7 miles of the main tube to allow technicians to operate at these heights. One can observe how the hydraulic manipulators place heavy steel arches to secure the ceiling against the weight of the mountain above. Therefore, the completion of this passage marks the transition to a new level of regional connectivity. The tunnel serves as a permanent bridge that remains open during the most severe blizzards, maintaining the flow of supplies and personnel throughout the entire year. This engineering feat effectively conquers the geological obstacles that once dictated the rhythm of life in the high mountains. The construction phase moves steadily toward completion, ensuring the road remains traversable in all weather conditions. From here, the focus shifts to the final installation of safety systems and lighting within the deep mountain passage. Thus, the transformation of the Himalayan transit route reaches a stage of permanent stability. 11,575 feet is the approximate elevation where the treacherous Zojila Pass carves its way through the rugged Himalayan terrain. Why is this specific mountain corridor considered one of the most dangerous lifelines on the planet? Travel across these winding peaks relies on hazardous roads that bridge the Kashmir Valley and the Ladakh Plateau, regions defined by vastly different climates. A delay of several seconds in a driver's reaction can be fatal on these narrow edges. But the geography itself creates an even greater obstacle, as heavy snow accumulation blocks the pass for 5 to 6 months every single year. This isolation leaves the plateau nearly cut off from the rest of the world during the winter. The pass has functioned for decades as the solitary route for the transport of essential goods, fuel, and military troops. At first glance, the path seems like a simple sequence of switchbacks, but in reality, it is a strategic bottleneck that dictates the survival of the northern frontier. One can notice how the landscape transitions from lush valley greenery to the stark, high-altitude desert of the plateau. It gets more complex further on. India launched the Zojila Tunnel project to bypass these seasonal closures through an 8.7-mile-long underground passage. This 2-lane road tunnel runs deep beneath the ancient rock mass to ensure year-round connectivity despite the constant threat of landslides and snowstorms. Temperatures frequently drop well below freezing, yet the construction process continues without interruption. The camera glides along the dark, damp surfaces where thousands of laborers work day and night in shifts. Because the elevation is so extreme, workers must operate in severely oxygen-deprived conditions that limit physical endurance. One can notice the constant shimmer of glacial meltwater seeping through the cracks of the 45-million-year-old rock formations. The process is only gaining momentum, Nearly $1 billion is the total investment required to pierce through the heart of the Himalayas. Large hydraulic drills penetrate the stone with a rhythmic mechanical vibration as reinforcement teams secure the tunnel walls. It seems like a standard engineering feat, but in reality, fighting the pressure of the mountain requires constant monitoring of the structural integrity. Travel time is reduced from 3 hours across the dangerous surface pass to just 20 minutes through the protected tunnel. This dramatic change establishes a state of permanent connectivity for the Ladakh region that was previously impossible. And this is not the limit of its impact. The project functions as a critical strategic infrastructure asset rather than a simple transportation link. It strengthens regional logistics and national security while fundamentally reshaping the geopolitical balance along the northern frontier of South Asia. The tunnel ensures that the flow of resources remains constant regardless of the weather conditions outside. Thus, the massive engineering effort concludes its primary phase, securing a stable path through the mountains. 11,500 feet above sea level is the staggering altitude where the execution of this massive infrastructure project unfolds within the formidable Himalayan range. Why is such an extreme elevation chosen for the construction of the Zojila Tunnel? One might assume a lower route would be more practical, but this specific trajectory is engineered to establish a permanent and unwavering connection between two isolated regions. But this is just the beginning. Atmospheric pressure at this height creates a punishing environment where the oxygen concentration is limited to only 60% of sea level norms. It seems simple to just deploy a standard workforce, but in reality, the thin air slashes human operational capacity and physical endurance to nearly half. Temperatures regularly plummet below -4 degrees Fahrenheit, while relentless gales and massive snow accumulations threaten to cut the site off from the outside world for months at a time. The equipment gradually becomes encased in ice if left stationary. Transition to the next level. One can notice how the initial phase of the project focuses not on the mountain face, but on the preservation of biological and mechanical life. Because the survival of the crew is paramount, engineers constructed specialized living quarters using highly insulated prefabricated modules. These structures are outfitted with integrated heating grids and supplemental oxygen injection systems to counteract the thin atmosphere. It is visible how medical personnel monitor workers for altitude sickness within these dedicated facilities. Everything only gets more complicated. A rotating shift system governs the movement of the labor force. Rather than the long-term site residency common at lowland projects, these teams cycle through brief intervals to allow their cardiovascular systems to adjust to the low pressure. In parallel, the camera glides along the perimeter where massive independent power generation stations operate in isolation from the local grid. This is not the limit. The regional electricity infrastructure lacks the stability required for 24/7 industrial operations, necessitating a fully autonomous energy source. The heavy machinery and life support systems thus remain powered regardless of the volatile high-altitude weather conditions. The foundational environment for the tunnel's breakthrough is now firmly established. 100% of the geological stress in the Himalayas results from the ongoing collision of tectonic plates, creating a mountain system that is still geologically young. Why can engineers not utilize massive tunnel boring machines here as they do in Europe or East Asia? In those regions, rock formations remain relatively stable, allowing machines to operate continuously without interruption. But in the Himalayas, the alignment runs deep within a landscape where ground conditions shift abruptly over very short distances. At first glance, the rock may appear solid, but within meters, it can transform into fractured strata, heavily weathered zones, or areas saturated by high-pressure groundwater. The process is only gaining momentum. Using a tunnel boring machine in such unpredictable geology is far too risky, as a sudden change in ground pressure or a massive water inflow could trap the equipment deep inside the mountain. This would bring the entire project to a prolonged standstill for months or even years. Therefore, the construction team adopted a flexible approach based on incremental steps rather than continuous mechanized excavation. One can notice how this method allows engineers to adjust their technical operations in real time based on the actual conditions revealed inside the mountain. It gets more complex further on. The excavation cycle begins with drilling small boreholes into the rock face. One can notice how the equipment gradually penetrates the stone according to precise survey data. Each hole is drilled at a specific depth and angle to ensure the rock breaks exactly as planned while maintaining the structural integrity of the surrounding mass. Controlled blasting follows this preparation, utilizing carefully measured amounts of explosives to minimize collateral damage. Why are the detonators not triggered all at once? Simultaneous detonation would create massive vibrations that could collapse the tunnel roof. To prevent this, the charges are fired in a rapid sequence separated by only a few milliseconds, which limits the transmission of shockwaves. Safety remains the primary focus. Immediately after the detonation, high-capacity ventilation systems are activated to extract thick clouds of rock dust, blast fumes, and toxic gases. In the oxygen-depleted environment of high-altitude mountains, the maintenance of air quality is a matter of survival for the crew. Only after monitoring instruments confirm the atmosphere is clear are workers permitted to re-enter the passage. The camera glides along the tunnel floor where the fragmented rock is cleared away to expose a fresh face. Temporary support measures are then installed to stabilize the sidewalls and roof, preventing the movement of the mountain during the transition to the next phase. Every 24 hours, the excavation face advances by more than 9 feet on average. While this figure may seem modest, it represents a carefully calculated pace in one of the most hostile construction environments on the planet. To accelerate the timeline, work occurs simultaneously from 2 opposite portals, allowing for the flexible allocation of heavy machinery and manpower. It is visible how the metal reinforcement lays in an even layer against the stone once the cycle concludes. This coordination between on-site experience and engineering adaptability ensures the tunnel grows steadily, despite the harsh Himalayan conditions. The fragmented rock is hauled away, and the mountain is secured for the next round of drilling. The molten energy of human effort continues to drive the project toward completion. Thus, the construction reaches a stable rhythm, moving the transformation into the final stages of structural reinforcement. 150 meters below the surface of the Himalayas, the variable geological structure makes time the most critical factor for maintaining tunnel integrity. Why must stabilization occur within minutes of a blast? The environment remains inherently unstable. If the freshly exposed rock surface remains unsupported for an extended period, the slightest vibration or a sudden surge in groundwater pressure can trigger immediate cracking or a localized collapse of the roof. The process is only gaining momentum. Stabilization begins almost instantly following the completion of each excavation cycle to prevent structural failure. One can notice how automated nozzles spray fast-setting shotcrete across the entire newly formed tunnel surface. Under low-temperature conditions, the chemical design of the concrete mix and its setting time are adjusted with jewelry-like precision to ensure it reaches the necessary strength in a very short window. It seems simple to apply a layer of concrete, but in reality, this is only the primary skin of the structure. At first glance, the rock appears solid, but internal stresses are constantly shifting. Long steel rock bolts are drilled deep into the surrounding mass to bind fragmented geological layers together. This creates a stable composite structure that allows the redistribution of the massive stresses generated during the removal of rock. The drilling equipment works with a rhythmic hum as it penetrates several meters into the mountain. It gets more complex further on. In zones characterized by weak geology or elevated risk levels, the construction team installs steel support ribs in a precise arched configuration. These heavy metal frames serve as a secondary reinforcement layer to preserve the tunnel shape against the immense weight of the Himalayas. One can see the ribs being positioned by hydraulic manipulators before being locked into place against the shotcrete wall. The combined application of sprayed concrete, deep rock bolts, and steel ribs allows for meter-by-meter control over the mountain. This systematic approach transforms a chaotic space disturbed by explosives into a controlled and safe environment. The material is ready to move to the next processing phase without haste. 32 degrees Fahrenheit is the critical threshold where liquid water transforms into a destructive force within the Himalayan rock mass. Why is the management of moisture considered a primary engineering challenge at the Zojila Tunnel? It seems simple to shield a structure with concrete, but the alignment of this passage runs directly beneath massive glaciers and fractured geological layers. Groundwater and meltwater from ice and snow seep through thousands of microfractures, creating a silent and constant hydrostatic pressure against the tunnel walls. The process of infiltration is relentless. one can notice how moisture does not only move in visible streams, but also permeates the material through invisible pores over long periods of time. This water accumulates within the structural elements, waiting for the seasonal drop in temperature. When the internal liquid freezes, it expands with immense force, generating internal tension that exceeds the tensile strength of the concrete. But this is just the beginning. Repeated cycles of freezing and thawing occur every year, leading to the progressive spalling of surfaces and a steady loss of the structure's load-bearing capacity. It only looks obvious that a tunnel should remain dry, but in reality, the harsh climate of the Himalayas makes this a complex hydraulic struggle. The long-term durability of the entire transit route depends entirely on the integrity of its barriers against this internal expansion. Engineers at the Zojila project implement specialized drainage and waterproofing systems in a synchronized operation with the primary excavation and surface support tasks. The equipment gradually installs thick waterproofing layers that act as a physical shield, preventing any moisture from penetrating into the deep structural lining of the tunnel. Seeping water is not allowed to pool. It is collected immediately at the tunnel invert. Everything only gets more complicated as the depth of the tunnel increases. Dedicated drainage pipes channel the collected meltwater out of the mountain interior with a steady flow. This combined engineering approach ensures that groundwater is controlled at the earliest possible stage of the construction cycle. One can notice the precision of the installation as the barriers are sealed to withstand the extreme environmental conditions. The result is a stable operating environment that remains unaffected by the severe thermal fluctuations characteristic of high-altitude mountain ranges. The drainage system operates continuously, ensuring the structural safety of the passage is maintained throughout the winter. Thus, the complex hydraulic management phase reaches its completion, allowing the tunnel to remain a reliable link through the mountains. 14 kilometers of mountain rock have been breached, and the primary stabilization of the Zojila Tunnel has reached its conclusion. Why is the construction of the tunnel invert considered the most critical transition after the initial excavation? It only looks obvious to focus on the ceiling, but in reality, the invert locks the entire geometry of the cross-section together. This heavy structural layer serves as a permanent foundation, designed to carry immense long-term loads and support every technical system installed above it. One can notice how the project shifts from the raw violence of blasting to the precision of infrastructure integration. But this is just the beginning. The focus moves away from advancing additional meters of tunnel toward the long-term goal of safe, controlled operation for several decades. Workers apply a comprehensive waterproofing membrane across the entire tunnel surface. It is visible how this barrier shields the structure from groundwater and aggressive Himalayan meltwater. Without this protection, the extreme climate would cause rapid freezing, corrosion, and structural deterioration. The process is only gaining momentum. A specialized lighting system now spans the full length of the passage. These units are engineered to operate reliably in a constant environment of dampness, cold, and drifting dust. This illumination does more than support daily traffic. It ensures that maintenance crews and emergency responders maintain perfect visibility at all times. Everything only gets more complicated as the climate outside changes. High-capacity fans replace the temporary ventilation used during the digging phase. The equipment gradually transitions into a permanent operational mode, featuring fixed ducting and automated controllers. These systems calculate the required airflow in real time, adjusting their power based on the density of vehicles and the changing internal air conditions. Transition to the next level. A dense network of safety sensors is embedded throughout the interior. These devices continuously monitor the concentration of toxic gases, smoke levels, and temperature fluctuations. One can notice how every byte of data flows instantly to a central control center for constant supervision. This lays the foundation for a reactive safety environment. If a fire or accident occurs, the ventilation system demonstrates its true power by rapidly reversing its airflow. It extracts smoke and searing gases from the impact zone, while simultaneously pumping fresh air into a dedicated evacuation corridor. It gets more complex further on. Surveillance cameras and emergency communication terminals are positioned at precise intervals along the walls. These tools allow for the early detection of any incident and provide direct guidance to drivers during a crisis. It is this specific combination of a durable structural shell and proactive technical systems that converts a void in the mountain into a reliable corridor. The Zojila Tunnel finally functions as a year-round transport artery, despite the harshness of the surrounding peaks. The transformation of the excavated space into a functioning infrastructure system is now complete. Thus, the steel and concrete reach the standard required for the final phase of service. 14.2 kilometers of solid rock are being transformed into a permanent passage through the Zojila Tunnel. Why is such an immense volume of material being hollowed out from the Himalayan massif? It only looks obvious to call this a transportation project, but in reality, it is a calculated struggle to stabilize an environment that is naturally hostile to any modern infrastructure. One can notice how every technical decision acts as a barrier against the extreme pressures of the mountain. This is where modern engineering begins to redefine how humans move through some of the harshest mountain ranges on Earth. Engineers start by establishing temporary living conditions and life support systems for thousands of laborers in sub-zero temperatures. The equipment gradually builds a self-contained ecosystem where air quality and internal climate are strictly regulated against the thin atmosphere outside. But this is just the beginning. Drilling rigs penetrate the rock face with the rhythmic hiss of hydraulics and the slow rotation of diamond-tipped bits. Controlled explosive charges are placed into the boreholes to fracture the granite without destabilizing the surrounding strata. One can notice how the dust slowly settles after each detonation, revealing a new section of the tunnel profile. Everything only gets more complicated. Massive steel ribs are positioned by manipulators to provide immediate structural reinforcement against the shifting weight of the peak above. It seems simple to blast and clear, but in reality, the installation of long-term operational systems must happen simultaneously with the excavation. Sensors monitor the structural integrity of the archway, while drainage channels are carved to divert glacial meltwater away from the roadway. The process is only gaining momentum. Thousands of tons of concrete are sprayed onto the walls to create a seamless waterproof barrier that protects the electrical and ventilation grids. Every individual step serves the single purpose of transforming a route that was once blocked by snow for several months each year into a reliable year-round transportation corridor. Transition to the next level. The final layers of asphalt and lighting systems are integrated into the deep mountain interior to ensure safety for future travelers. The metal and concrete structure quietly settles into its permanent position as the construction phase nears its conclusion. From here, the transformation moves to the next phase of processing and final integration into the regional network. 11,575 feet above sea level, the Zojila Pass stands as a physical manifestation of the brutal environmental challenges imposed by the Himalayan range. Why must engineers attempt to conquer such a vertical and unpredictable landscape? It only looks obvious to accept the seasonal isolation imposed by heavy snow, but in reality, the Zojila Tunnel serves as a decisive response provided by modern heavy engineering to bridge this gap. Instead of allowing nature to dictate terms, the strategic decision was made to drive a subterranean path straight through the mountain rock. This ensures the continuous flow of transportation, military logistics, and essential supplies across the region. But this is just the beginning. The Zojila project does not merely alter the local transportation map by reducing travel time from hours to minutes. It fundamentally reshapes the technical methodology of how humans approach some of the most rugged and unstable terrain on the planet. One can notice how the reinforced tunnel walls maintain structural integrity against immense lithostatic pressure. Everything only gets more complicated when considering the broader context of the regional development. The Zojila Tunnel is not a standalone achievement functioning in isolation. It represents a single critical link in an extensive chain of infrastructure works where engineers choose to penetrate high-altitude mountains and span deep valleys. At first glance, the construction seems like a series of disconnected sites, but in reality, it is a unified effort to build in locations once categorized as geographically impossible. The equipment gradually moves deeper into the granite heart of the range, with hydraulic drills operating at constant high pressure to clear the path. The process is only gaining momentum. Each meter of excavated rock brings the two sides of the valley closer to permanent connectivity. One can notice how ventilation systems and drainage channels are integrated into the tunnel floor to prevent the accumulation of hazardous gases or groundwater. Large-scale manipulators install heavy concrete segments along the arch to stabilize the ceiling against potential seismic shifts. It is visible how the interior surface is smoothed and sealed to to withstand the extreme temperature fluctuations characteristic of the high Himalayas. The camera glides along the length of the excavation, where the scale of human ambition meets the raw resistance of the Earth. From here, the transformation moves to the next phase of processing as the tunnel prepares for the final installation of safety systems and lighting. Thus ends one of the key stages of this massive high-altitude engineering endeavor.